I'm going to go back to algebra class. Regular algebra class, not even linear algebra, some crazy algebra, regular algebra class. And ask you to remember elimination by addition for simultaneous equations. This is why having an algebra tutor as your pastime ain't a bad idea, because we're going to use the same stuff. But I'm going to change the way we write derivatives a little. Operator versions of derivatives means we write a derivative like we're doing something to a function. So instead of writing y prime, I write d of y. Instead of writing y double prime, I think of the derivative, right? So I'm just going to write that as d squared y. That's a second derivative. By the way, if I want to think of y itself, I can think of the operation of multiplying using the identity operator. So I can think of this as like 1 times y. Now, when we do simultaneous equations, hang on a second, I got to go back to that algebra class again. Remember crap like this? If I want to do elimination by addition, how did we do that? How did I eliminate in a setup like this? I multiply by whatever is necessary to cancel out a variable. Exactly. So in this case, I could multiply the second row by -2, and I would cancel the x's. Or I could multiply both rows, right? Multiply the top row by 5 and the bottom row by 3, and then I'd be able to cancel the y's. I want to think of the same procedure, only I'm going to think of derivative operators instead of multiplying. That sounds weird. Let me write up a set of first order differential equations. With me so far? Yes, sir.
Good.
On the top, it's X prime. For me to have a system of first order differential equations, I have to have a derivative for X, I have to have a derivative for Y in each one. So, I want to turn those equations into things that look like the algebra equations above it. So let's put all the variables on one side. And we'll group variables in the same order. So I'm going to think of this first equation as x prime minus 2x plus a y equals 0. And then down on here, I'm going to put the minus x at the beginning and then plus y prime equal to 0. Wait a second. Operator notation. I did say I wanted to do operator notation. So I'm doing operator notation. X prime becomes, only I'm just going to write dx, right? D is like being multiplied here. It's operating on, but I'll write dx minus 2x plus y. And what about the second equation? Now, here's an idea similar to Laplace transforms. The operator of doing the Laplace transform could be split up. Or it could all be grouped together, right? We were able to take the Laplace transform of a whole bunch of stuff, or we're able to do it all separately. Yes? This first equation, those two terms are both things that are acted on x. I have the derivative x, and I have multiply x by 2 and subtract. I can think of combining the operators and writing this part of this equation, d minus 2, operate on x. With me so far? This now looks like thing times x plus thing times y equals number in both equations. Let's eliminate something, which means I need to multiply a row by something. Only multiply a row here means use one of the d things to operate. If I took that top row and I said what I'm going to do is I'm going to put a minus d there. Or even a plus d, right? I could do it either way. I'm going to multiply by d on the top row. I'm going to multiply by minus 1 on the bottom row. What are your two new equations? Well, let's leave it factored for the moment, but yes, d squared minus 2d equals 0. And on the bottom, But I like thinking of that like it's d squared minus 2d. Elimination by addition. What happens if you add? Well, you get d minus 2x minus plus x equals 0. And if Jalen, if I do exactly what you suggested, excuse me, and I write that as d squared minus 2d, there's also this other x, isn't there? If I factor that x out, what's inside that set of parentheses? Guess what? That's a second order differential equation, isn't it? This equation right here is the same as y double prime minus x double prime minus 2x prime plus x. I know how to solve that. But I don't actually need to convert it to a differential equation to do that. Because if you were going to solve this the way you did on the last exam, what would you do? Second degree equation equal to 0. It's homogeneous. What do? And isn't that going to give me a quadratic? Isn't it going to give me this quadratic? Only in the letter R instead of in the letter D? I've already got the equation I need. It's sitting here. There's my equation. What are my two solutions? Which means it's a repeated root. So I'm going to get x of t is c1 e to the t plus c2, what's the second part? I just figured out x. How do I figure out y? Just something up here, right? I go back to one of the previous equations. Oh, the previous equation says x minus dy equals 0, which is the same as saying that x is the derivative of y. So if I want y, I just have to integrate x. I got it. So that's the integral of c1 e to the t plus c2 t e to the t dt. Oh, I got to do integration by parts. I'll live. C1 e to the t, C2, I do integration by parts. U dv, u equals t, dv equals e to the t. So v is e to the t, and du is just dt. So I get uv t e to the t minus the integral of v du. That's the integral of e to the t. What's the integral of e to the t? Yay. Please notice that what I get is C1 minus C2 e to the t plus C2 t e to the t. Except I forgot something. What did we forget? a plus C somewhere, right? I integrated. There's got to be a plus C. I have too many C's. We'll call it something else. Plus K. I think that may or may not be 0. I don't know. It might be a number. It might be 73. I have no way of knowing. But I could check. How? Isn't that how I got this in the first place? That's not to say you're wrong. You're absolutely right. But I need to plug it back in to the other equation that I haven't used yet. So I need to take this first equation, which was x prime equals 2x minus y. All right, wait a second. What's x again? Right, x was up there. Let's figure out what's x prime. X prime equals. X is C1 e to the t. What's the derivative of that? The derivative here. C1 e to the t. The derivative of this part requires me to use the product rule. So I get C2 e to the t plus C2 t e to the t. Yes? And then I can figure out what 2x minus y is using these expressions. See where the k is? Multiply out and simplify all this garbage on the right. Tell me what you get. We'll group by e to the t versus t e to the t. In the first set of parentheses, I have 2c1 e to the t. The second set of parentheses, I have c1 minus c2 e to the t, which is being subtracted. So it's minus c1 plus c2. For the t e to the t's, I have 2c2 of them. And then I have minus c2 of them here. Oh, that's a minus k. There. What's the simplified thing inside the first set of parentheses? Inside the second set of parentheses? This should be equal to that. The only way those are equal is if k is 0. I got lucky because when I set up the equations in the first place, I had a 0 in it. And that made this simplify out nicely. But the best part about this goes back to regular ordinary elimination by addition. I like this. I can do elimination by addition till the cows come home. And when I do that elimination, I end up with a straightforward single variable differential equation. Not a system. I reduce it to one differential equation. So just like in algebra class, I have two equations in two variables. Mush them together to make one equation in one variable. Solve that, go back and find the other one. Sound reasonable? We'll do more. We'll practice. This problem is not homogeneous. So how do I rearrange it? To write it in operator notation with the variables x and y on one side and the t's on the other. What's my new version of the equations? Yeah, but I kind of want to line these things up. So I'm going to write dy here and negative x there. I don't have a problem with doing it either way. It's your call. I just happen to think aligning all the variables makes my life easier. Just like I was doing in linear algebra, just like I was doing in regular algebra class to do simultaneous equations, lining stuff up helps me out. Okay, what's our elimination by addition step? What do you want to get rid of, x or y? Which means I need to cancel that with this. So I'm going to multiply both rows again. I'm going to multiply the top row by a d. I'm going to multiply the bottom row by -1. Now here is a neat occurrence. On the bottom row, I get x minus dy equals positive t. What do I get on the top row? Well, that'll be d squared, right? Yes, but there's no extra x because it's a derivative of t. right? X is a function of t, y is a function of t. T is my independent variable here, not x nor y. They're both functions of t. Keep going. I'm taking my derivatives with respect to t, so what happens on the right? I get a 1. D is with respect to t. WRT, with respect to, shorthand. Okay, wait a minute. What's my elimination result? Or d squared plus 1 x equals t plus 1. What's the quadratic equation that goes with this? Remember, this is a non-homogeneous one. I have to solve the homogeneous one first. Because if I want to do anything with t's on this side, I got to do it with a 0 on this side first. What's my quadratic? Right. So the quadratic equation is r squared plus 1, isn't it? And when I set that equal to 0, what do I get for r? Which means I get cosines and sines this time, right? Oh, x equals c1 cosine t plus c2 sine t. But that's the corresponding homogeneous part, right? This is really xc. Now I need xp. How do I get the particular solution? Well, I think the right-hand side is really easy. It's 1 plus t, right? So we'll use a linear equation. And we'll use undetermined coefficients. xp is a plus bt. And that means that xp prime is b and xp double prime is 0. So I get to plug those in here. X double prime plus x equals 1 plus t, right? But wait a minute, x double prime is 0. X a plus bt equals t plus 1. A is 1, b is 1. Which means I now know x of t. C1 cosine t plus C2 sine t plus t plus 1. Or plus 1 plus t. How do I get y? I could, but please notice what my other equation looks like. What was the other equation? Which is the same as saying that y equals negative x prime plus t. I don't actually have to do an integral this time because I can do a derivative. That's this equation instead of this one. Now, if you did it the way you want to, excuse me, well, I can get a different answer depending on which way I do it. So let's take a look at this. What happens when you do this? What's x prime? And then what do I do with that? Hmm. Y prime equals x minus t, right? If I did that, well, then I'd take x and I'd subtract away the t, and that would say that y prime is c1 cosine t plus c2 sine t plus 1. So what's y? According to this. Just to distribute the negative sign. Yes, I absolutely do. Good catch. That's going to make a difference now, isn't it? Never mind. Never mind. I'm looking at this and I'm going, I have a sign error. I have a plus y. I should have a minus 1. I forgot to distribute the negative. Good catch. So that gives me C1, negative C1 sine t minus C2 cosine t minus 1 plus t. The minus 1 was the thing that was giving me fits because I did it the other way on my notes and then realized I could do it this way. I forgot to write it down the other way, but this works. So skip that part. That's more work. I don't want to do integrals if I don't have to. I like not doing them. Thank you. Sitting here beating my head against the desk going, why is this wrong? Did I already screw that up again? X prime, derivative cosine is minus sine. The derivative sine is cosine. So yes, the sign should be positive because the minus was already in there. Geez, Josh, you're not getting anything right today. Compound my sign errors. Mia, you're looking at this like I just slapped you with it. Talk to me. I forgot to put the minus sign from here. And because I forgot it, I screwed up the entire signs on those last lines, and that's me on. Thank you. Clearly, it's a Friday at 3 o'clock, right? There are several examples. Page 185 has a couple of them. This one, I did a couple different ways. But you'll notice when we do this, we end up with 4 different constants. They solve for y by elimination. They solve for x by elimination. They do them both separate from one another. They eliminate to get x, they eliminate to get y, and that gives me 4 different constants. I hate that. That's why I only do the elimination for one of them and then go back and figure out the other one from that. That's not what was done here. So I think you ought to look at this one and then try and do it the way we just did the 2 examples we've done so far. Page 185. Questions? This was a non-homogeneous one. The first one was homogeneous, but these both had something in common. 2 equations and 2 variables. Ain't no reason not to do more. 3 equations, 3 variables. Problem number 17. First thing I'm going to do before I do anything else is I'm going to write it aligned. So I have dx minus y equals 0, dy minus z equals 0, and minus x plus dz equals 0. And now we get to do some choosing. Because if I go back to my algebra class and I think about 3 equations and 3 variables, what we did was to pick 2 of the equations and get rid of 1 variable, and then do the same getting rid of a variable in one of the other equations. So I look at this and I go, this sucks. But equations 1 and 3 contain all 3 variables put together. There's an x and a y in 1, there's an x and a z in 3, but there's only a y and a z in 2. So what if I took 1 and 3 and got rid of the x? Let's do that. What do I get? There's my first equation. What do I do to the second equation to get it to eliminate? The equation number 3 to get it to eliminate. Okay, so I'll have minus dx plus d squared z equals 0. And when I add, I get minus y plus d squared z equals 0. I'm going to call this equation number 4. I'm going to go back up to the original set, and I'm going to label equation number 2, which I didn't label in the first place, which was dumb of me. Should always label the equations. Now take 2 and 4, because they're in y and z. I have dy minus z equals 0. I have minus y plus d squared z equals 0. What are we going to do? Okay, so that'll give me dy minus z equals 0, and then minus dy plus d cubed z equals 0. I eliminate, and I get d cubed minus 1 z equals 0. A third order differential equation. But I know how to solve that. R cubed minus 1 equals 0. What does that factor by? It's got to factor into something.
R minus one.
Yeah, I was going to say it's R minus 1 and something, right? I can do it the hard way. R minus 1 into R cubed minus 1. I can do the division. Hey, if I'm stuck, it's the easiest thing to do, right? R goes into R cubed, R squared. So I do R squared times R, which is R cubed. R squared times 1 is R squared. I subtract. I get R squared. R goes into R squared, R. I get R squared minus R. I subtract. That gives me an R. Bring down the minus 1 because now I'm in the right spot. Hey, that's a plus 1. R minus 1. I subtract. It cancels. So this is R squared plus R plus 1. There is a formula for the difference of two cubes. That's it. But I can never remember it either, so I always do it the hard way. Long division was a long time ago, man. We did it for slant asymptotes in Calc 1. We did it for the division algorithm in discrete. Y'all have seen this before. You did it in abstract if you took that already. Hey, wait a minute. This gives me R equals 1. I got to do the quadratic formula on this one to get those. Because that one's not going to factor nicely. Do the quadratic formula. Tell me what you get for those two. Jay, there's a faster way if I do this in complex numbers. I can do the whole thing, cube roots of 1 as the roots of unity. Remember that? I know she taught it to you.
Friday.
Yes, it's Friday. So the answer when I do the quadratic formula is I get negative 1/2 plus or minus root 3 over 2i. Which means I have C1, C2, C3. I have C1 e to the t, C2 e to the minus 1/2 t cosine root 3 over 2t, and C3 e to the minus 1/2 t sine root 3 over 2t. And this is z. Now what? Well, now I'm going to do the same thing I did in the last problem, because if I go back up to the original equations, I know that x is the derivative of z. And I know that y is the derivative of x. So I don't have to do any more integrals. I just have to do two sets of derivatives. Because I have z, I can get x. Once I have x, I can get y. And then I will have solved this completely. I got all three equations all set up. And I never had to do an integral. And I'm really happy about that, because doing integrals with e's and sines and e's and cosines makes my head hurt. Those are disgusting, and I don't want to go. These problems are not short. But look at what we are using. We're using nothing more than an algebra trick from simultaneous equations and the crap we did in chapter 4 and chapter 3. I know how to do this. It's just, I got to do all of it. Not, I can do this and it's done. Well, damn. Again, I replace a lot of calculus with algebra techniques. So what happens if I do my favorite replacement of calculus with algebra techniques and start thinking about this in terms of Laplace transform? By the way, the third video in the series on Laplace transforms came out on 3 Blue 1 Brown Thursday. I haven't watched it yet. I think it's the first two were spectacular, so I think it's worth watching. I'll be watching it this weekend. I think you all should too. But we will talk about doing Laplace transforms on systems on Monday. I will see you all then. Enjoy your weekend.